AIME 2019, Problem 11. At first glance, the 10th and 12th powers of trigonometric functions suggest a computational nightmare. However, in mathematics, whenever a problem appears brute force heavy, there is almost always a deeper structural symmetry waiting to be exploited.
We are given that the sum of the 10th powers equals 11/36. Our objective is the sum of the 12th powers. Notice the pattern. We are dealing exclusively with even powers. This is a vital structural hint. I often see students attempt to expand the 5th power of the Pythagorean identity to isolate these terms. I remember attempting a similar brute force expansion in my youth. It was a regrettable waste of ink and paper. The expansion generates 6 terms, 4 of which are cumbersome cross products that obscure the underlying identity. The mathematically mature approach is to derive a recurrence relation. This establishes a rigorous functional mapping between consecutive even powers, allowing us to transition from the 10th degree to the 12th with absolute precision.
The complexity of trigonometric expressions often stems from the transcendental nature of the functions. By shifting our perspective to algebra, we eliminate the transcendental overhead and expose the underlying structural symmetry.
I define S as sine squared x and C as cosine squared x. I utilize the square specifically to invoke the Pythagorean identity, a fundamental principle of Euclidean geometry that remains our most reliable constraint.
In this notation, the identity S plus C equals 1 effectively reduces our system's degrees of freedom. In any rigorous derivation, simplifying the variable space is the first priority.
Next, we define the product as P. In the theory of symmetric polynomials, the sum and the product are the elementary building blocks used to construct all higher-order power sums. Observe the mapping. Since sine squared is S, sine to the 10th is simply S raised to the 5th power. We have transformed a transcendental problem into a polynomial relation, which is significantly more tractable.
Our objective is to determine the 6th powers. Precision here is paramount. In my experience, even a minor error in definition will propagate through the entire derivation as complexity increases.
We shall adopt the notation S sub k, the convention for Newton sums. Our reformulated problem is now mathematically precise. Given S sub 5 equals 11/36, find S sub 6.
The instinct of the amateur is to solve for S and C using the quadratic formula, but introducing radicals is a form of algebraic violence that destroys the symmetry we have cultivated.
We do not need the numerical values. We need the law. If S and C are roots of a quadratic, then they are logically bound by its characteristic equation. François Viet, the father of modern algebraic notation, showed us that a polynomial is built from its roots. Expanding t minus s times t minus c reveals the structural connections.
Viete established that the linear coefficient is the negative sum of the roots, while the constant term is their product. This is not a coincidence. It is a structural necessity.
Substituting our specific constraints, we derive the characteristic equation, t squared minus t plus p equals 0. This identity governs every power in our system. By isolating the leading term, we see that t squared is simply t minus p. We have expressed a higher power as a linear combination of lower-order terms. To generalize this for any power k, we multiply the entire identity by t to the power of k minus 2. This shifts our structural law across the entire sequence. This yields a second-order linear homogeneous recurrence relation, a single recursive rule that dictates the infinite progression of powers. Because S and C are the roots of our original equation, they are logically compelled to satisfy this identity. Mathematically, they have no alternative. Finally, we exploit the principle of linearity. Define S sub k as the sum of these powers.
If S and C satisfy the recurrence, then their sum must also satisfy it. S sub k equals S sub k minus 1 minus p times S sub k minus 2. We have bypassed the messy arithmetic of radicals entirely. This is the efficiency of pure logic. Expanding a 10th-degree expression via the binomial theorem is a task of extreme algebraic burden and inevitable arithmetic error. A recurrence relation is a logical vacuum without its initial conditions. S0 is the sum of variables to the 0th power, 1 plus 1, which is 2. S1 is the Pythagorean identity, sine squared plus cosine squared, which is 1. S2 is defined as S1 minus p times S0. Substituting 1 and 2, we obtain 1 minus 2p. Notice how the structure remains clean, avoiding messy trigonometric expansions. For S3, we take S2 and subtract p times S1. Substituting 1 minus 2p and 1, we simplify to 1 minus 3p. Each rung of this ladder is supported by the one below it. At S4, the quadratic dependency on p manifests. We take S3 and subtract p times S2. After careful distribution and combining like terms, we arrive at 1 minus 4p plus 2p squared. Finally, we reach S5, our 10th power sum. One final reduction using S4 and S3 yields 1 minus 5p plus 5p squared. We have bypassed pages of expansion with a few lines of logic. We have mapped a 10th-degree transcendental expression to a simple quadratic in p. This rigor is the ultimate labor-saving device in mathematics. Theoretical beauty is one thing, but the ultimate test of any derivation is the transition from abstract identities to concrete numerical solutions. By substituting 11/36 for the 5th power sum, we finally confront the quadratic reality of p. I find that students often rush this stage, but standard form is non-negotiable for clarity. By consolidating the constants, we arrive at 5/36, a necessary arrangement for the next logical step. Notice that every coefficient is a multiple of 5. We divide the entire equation to produce a monic quadratic. In mathematics, reducing complexity at every opportunity is a mark of professional discipline. Applying Vieta's relations, we seek two numbers whose sum is 1 and whose product is 5/36. Testing the factors, we determine that 1/6 and 5/6 are the unique solutions. Now, the algebraic work is done, but the mathematical work is not. We must verify these candidates against their analytical constraints. Because p is defined by trigonometric functions, it cannot take just any value. Recall that p is the product of sine squared and cosine squared. By utilizing the double angle identity, we can see that p is exactly 1/4 the square of sine of 2x. The range of any real sine squared function is strictly bounded between 0 and 1. Thus, p must reside within the interval from 0 to 1/4. Visualization is the bridge between algebra and intuition. By plotting our roots on a number line, the conflict between our candidates and the domain becomes immediately visible. 5/6 clearly exceeds our upper bound of 1/4. It is an extraneous root, an artifact of the algebra that has no place in the trigonometric solution. We must reject it without hesitation. 1/6, however, is perfectly situated within the bounds. It satisfies the algebraic equation and the analytical constraints simultaneously. This is our verified value for p. Early in my career, I once failed to check the domain of a complex fluid dynamics proof. It led to a physical impossibility. Since then, I treat rigor not as a burden, but as the only safeguard of truth. Isaac Newton's work on symmetric polynomials provides us with a surgical tool to avoid the brute force expansion of binomials. Now, we perform the rigorous numerical execution. To calculate S sub 6, we require S sub 5 and S sub 4. We already have S sub 5 as 11/36. For S sub 4, we use our previously derived formula.
1 minus 4p plus 2p squared.
Substituting p equals 1/6, 4 times 1/6 is 2/3, and doubling the square of 1/6 yields 1/18. Consolidating fractions with a common denominator of 18, we find that s sub 4 equals 7/18.
We now apply the recurrence relation one final time. S sub 6 equals S sub 5 minus p times S sub 4. Every step has led to this exact structural alignment.
Inserting our values, s sub 5 is 11/36, p is 1/6, and s sub 4 is 7/18. Converting to a common denominator of 108, we have 33 minus 7, which yields 13/54.